Okay, everyone, so it's time to start now. And I just want to remind you that you have homework due tonight. And everyone should really do this bonus survey. It will take you literally 2 minutes. And we're going to analyze our own data starting next week. So try to do that. It'll be more fun for you, plus it's worth bonus points. The only reason people don't do it is they forget. And then next week's homework's due Tuesday and Thursday. I might just change those due dates. I'm not sure. Seems like, we have Monday, Wednesday, and Friday classes, Tuesday and Thursday classes, and to keep everybody together, we might have to do that. So for next week, and maybe for the foreseeable future, it will be Tuesday and Thursday at 11:59 instead of Monday and Wednesday. And homework 5 is now posted, and you'll be able to do most of it after this lecture. So let's go to the document camera here and start. And we're starting right now. We've just finished probability, and we are starting. That's going to show me, right? Okay, I have it. Here we go. So here we are. We're on chapter 8. Let's just focus. And we finished probability, and now what are we doing? We're doing these statistics for random variables because we're going to be looking at random variables. We're going to be looking at numbers generated by a chance process. For example, sampling from the population and trying to infer from our sample the population parameters. Random division into 2 treatment and control. We're going to be analyzing, we're heading into inferential statistics, and we're going to be analyzing, looking at the statistics for random variables. So how do we do that? We do that by translating the chance process into a probability model, which is just a simple box model. And these random variables are just numbers. Don't get confused by it. It's just numbers generated by a chance process. Instead of just looking at a list of numbers generated by a chance process. For example, sampling a random sample from a larger population. Instead of just, so far, we've been doing descriptive statistics. So we're heading into inferential, so we need to make these underlying probability models that you see that are the basis of inferential statistics explicit. And that's a theme of this course, to show you what you're doing, what's going on underneath all the statistics. We're actually basing them on a probability model. Somebody had a question, yes? Oh, on the previous page, good question. We skipped something. We skipped these 2 right here. Is that what you're talking about? I posted these 2 on the, when we skip problems, I go through them all and I post them on the lecture video. So you can take a snapshot of this now if you want right now. But we covered this already. But I go through it in detail on the lecture video. Do you know that all of you can, right after class, look at the video? And if I don't cover it in class, I make my own little video and post it there. Or if we have technical difficulties. Does that answer your question? Yeah. So everybody do that. All right, now, so here we are back here. And so the simplest probability model is just something called a box model where what are we going to do? We're going to take basically tickets. On each ticket is written a number. And then we're going to specify, we put these numbers in a box. You shake them all up so that we're going to just pick random numbers out of there. And we're going to specify, so each ticket has a number written on it, how many draws we want to be made from that box, and whether we want them with or without replacement. When you take a ticket out of the box, you're going to put it back or not. So now let's just start making these super easy box models. And here's a big hint that it's always simplest to think about making the box model for a single draw. So you're going to, this is preparing you for when you want to use statistics on real life problems. They're all based on some underlying probability model. So you're either going to use the mathematics to figure that out of probability, or else you can simulate that underlying probability model using a computer, right? Make that and simulate it, but you have to get to that step. And so often in statistics, that step is ignored, and it's becoming increasingly important as you're going to have to create your own probability models. And now that you have computer power, and do simulations, and that's really fun. But if you don't understand how to do this and don't get used to doing it, you're just going to rely on these formulas that aren't perfect. They're math, and they don't fit the real world perfectly. So this is useful. So we're just going to start off really easy. So make it for a single one, okay? So create a box model for counting the number of heads in 10 tosses of a fair coin, all right? So first of all, what's the random variable? Well, the number of heads. That's going to be varying from, you could get 0 heads all the way up to 10. All right, so that's what this is right there. And so now, before we even start, just make a box. I want you to actually draw a box, okay? There's your box. And I want you to have tickets in it, okay? Now, make this box, we don't know how many tickets yet, I just put 2. Draw the box for a single toss, for one toss of the coin, even though we're tossing it more. Okay, so on one toss, you can either get a head or a tail, but we need numbers on the tickets. And what are we doing? We are counting. So we count by ones. So if we get a head, we're going to count it as 1 head. And if we get a tail, we're not going to count it as 1 tail. We're going to count it, we're counting heads. We're going to count it as 0 heads. So that's the head and that's the tail. And so that's our box. Each ticket has a number written on it, right? Now you could make it, this has 2 tickets, okay? So instead of, this simulates a coin. Now we're going to draw randomly from this box. It has a 50-50 chance, a fair coin. And how many times are we going to do it? We have 10 tosses, so this tells you how many times. So we're going to draw 10 times. From that box. And so let's say we drew once. We got a 1. That means we got a head on our first toss. Well, then obviously we're going to put that 1 back. So the next time we still have a 50-50 chance because it's simulating a real coin, a real fair coin. Okay, so it's 10 times with replacement. And then what? And then we're going to get numbers. We could possibly get all ones. That would mean we got 10 heads in a row. Or all tails. That would get 0 tens, or any combination of those. So draw 10 times with replacement, and what do we want to do? Take the sum, just count up, of the draws, of the 10 numbers. And that simulates tossing a fair coin 10 times and counting the number of heads. All right, so let's go to an iClicker, and I'm going to ask you to make a box model. Okay, so let's do that. Okay, we'll start it. Can't really see that. So rolling 2 dice and counting the total number of spots corresponds to the sum of how many draws with replacement from which of those boxes. Remember, pick the box for just a single toss and think what you're doing. Okay, has everybody chosen? We're going to stop it now. and see what people chose. Okay, that's correct. D is correct. Let's see why. Okay, so you want 2 draws. Well, they all say 2. And we're actually paying attention to the number of spots. So you could get, don't pick this one draw with 11. The possible sums you can get are 2 to 12. You can get 2 1s, which would be 2, or 2 6s, which would be 12, but they're not all of equal probability. The most common, is getting what? A 7. We saw that last time. So this is out. That says they're all equally likely. This one. So D is correct, because each die has this probability. Great. Let's see if we do we do another one? Let me just see. Okay, how about this one? All right, is everybody almost done here? Just pick one of these. It's okay if you get it wrong, just pick what you think it should be. Okay, I'm going to stop it now. And, all right, let's see which one you picked. C, that's correct. Okay, let's see why it's C. All right, well, what are we doing here? What we're doing is we're just counting whether, you might think it's this one, that's what some people picked because that resembles a die. But all we care about is counting whether you got a 2 or not. So if you get a 2, we're going to count it as 1, 2. And every other one of the 5 numbers count as 0 2s. So this is your box. All right, let's go to the document camera. Yes? You're counting the sum of the 5 draws. So, because you're counting up the number of 2s. So, if you do it 5 times, and let's say you got a 2 each time, you'd have 5 1s. We're going to do the example right on the paper so you'll understand it here. Okay, so let's go to the document camera. And right here, it's a similar one. Let's just look at this. Okay, so create a box model for counting the number of 2s that appear not in 5 rows. Here it says 20 of a fair 6-sided die. So what's the random variable here? Well, that's just the number of 2s. That can vary from getting 0 all the way up to getting 20 2s. So remember the hint. Draw the box for one roll, one play. All right? Just one. So you might think, okay, let's just think about it. So there's going to be 6 tickets in here. And what are we doing? We're just counting the number of 2s. So if we got 1 spot, we count it as 0 2s. If we got 2 spots, we'd count it as 1 2. And everything else would count as 0 2s. 3 4. Does that make sense to everybody? That it's just one. You're thinking, I can draw, the die looks like this. You have 1 spot, and you have 2, 3, 4, if this helps you, 5, and 6. That's what it's going to look like. Now, if you get this, you're going to count it. All we want is what we're doing is counting the number of 2s, and we count by 1s, 1, 2, 3, 2, etc. So if it looks like this, you're going to count as 0 2s. Here you got 1 2. Here you got, on one toss, here you got 0 2s, 0 2s, 0 2s, and 0 2s. So that is your box. And an easier way of writing that is, because we don't want to be drawing that all the time, is you can say, okay, the box has 1s and 0s in it. And you can put above it, there's one of these and 5 of those, and it still has 6 tickets. That's the shorthand way of writing it. Okay? And so then what are we going to do? Well, we're going to 20 rolls, so we're going to draw 20 times. And that means we're going to have 20 numbers. Some of them will be ones and some of them will be zeros, and just sum them up. When I say draws, I mean you get a draw and you get a 1 or a 0. Okay? Does that make sense to everybody? And it's with or without replacement. We want the die has the same chances each time, so draw 20 times with replacement. All right, so let's do, now what we're going to do is, on the next page, is we're going to look at the average and the standard deviation for these random variables known as the expected value, because it's going to change every time. What do we expect to see on the average? It's the expected value and the standard error. There's going to be error around that. But first we're going to start with the sum, and then we'll do the average. Okay? So the expected value for the sum and the standard error for the sum. So previously, we numerically summarized a list of numbers by computing their average and standard deviation, and then we graphically summarized them, what? With a histogram, right? Now we're going to be doing the analogous thing for numbers generated by a chance process, random variables. Okay? That's what we're going to be doing, and they're going to be called the expected value. So here, instead of, we'll call it the expected value for, and this is the standard error, and it's for random variables, okay? The expected value. This is going to be for random variables. What do you expect to see? And your error around it, like your sampling error. Instead of, it could be called a standard deviation, but I prefer to call it a standard error because you expect something, and then you have some sampling error around it. Each time you're going to get a chance error, either above that or below that. So it's like a standard deviation for random variables. Okay, so now, so we could get the expected value for any of these 3 statistics we're interested in. The sum of the draws, the average of the draws, or the percent of draws. In classification models, like percent, if you have zeros and ones, what percent of the ones do you have, what percent of the zeros, etc. So the sum, we're generally interested in gambling games. Remember, we're translating chance processes into these box models. So gambling games is generally where you'll see this, or maybe your score on a multiple choice test, something like that. Like it could, the sum of the draws could represent your winnings or losses in some gambling game, or your score on a multiple choice test if you're guessing on all the answers. And these two come up much more often, and they come up generally in surveys or sampling. Okay, sample surveys. You know, if you took a survey to estimate people's average income generally, or their average blood pressure, you wouldn't want the sum total of all their blood pressures generally. Or you might want the percent of people who are going to vote for Trump, and then you'd count the percent. You wouldn't count the sum total generally. Okay, so the idea is, this is what we're doing, obviously, but it spells it out here. The sum of n draws from a particular explicitly specified box is going to vary each time, because when your sample is going to change each time, just depending on the luck of the draw, right? So we need some way to quickly describe the distribution of all the possible sums. What you'd expect the sum to be, that's the expected value. What you'd expect the average or the percent to be, and how far off that's likely to be. That's the standard error. And that's what we're going to do in this chapter. And then in chapter 9, which I hope we get to, we are going to draw probability histograms that will display all the possible sums you can get and the likelihood of the probability of each one. Okay? So first, let's just start off with this expected value and standard error for the sum. Okay? So let's say, here's an example where you have this box right here, and it has these 5 numbers on it. All right? So the 100 draws are made with replacement from this box containing these 5 tickets, and you compute the sum. Now think about what the smallest the sum could be. If you got all 2s, right, and n is 100 here, that's your n, that's how many times you're drawing from there. So if you got all 2s, it would be 200. And what if you got all 6s? Well, then it would be 400. So that's the minimum and that's the maximum. But what would you expect the value of the sum to be? Well, the expected value for your sample sum, we could get any, what do we expect means sort of like in the long term, what would the average sum be? We call it the expected sample sum. So the expected sample sum is equal to, what do you think? Well, first of all, you'd expect to get, not the lowest or the highest, but on average, the average of this box. So the average of the box here is what? The average of this box is 4. Good. Symmetrical, and it's 4. What did you say?
Is that wrong, like the 400? Is it 6 times 100?
Oh, yes. Duh, thank you. I love having you here. See, when I do this on my own, if I just do this, I make mistakes like that because I'm thinking ahead to the average. And so I really appreciate you guys, because otherwise I have mistakes. All right? So that's 600, of course. And so now, so what is the expected value of the draws? Well, the expected value is going to be n, which is 100, right? That's the number of draws times the average of the box, which is 4, so it's 400. Okay? So the expected value is going to be n times the average of the box, which is equal, this is the number of draws, so that is 100 times 4, which is 400. So that's your answer. Any questions on that? Now you might want to say, since you can think of the box as the population, because so we can think of this as mu, and then we could call it mu and could say that's 4. And then each time we get a different possible sum, we could, particular samples average would be x bar. All right, let's move on. And now, let's look at this next example. And please, if I make even whatever error I make on here, please tell me. We want these notes to be perfect, and I need your help. I should start giving extra credit for any mistake I make, except if it's super minor, like I didn't put a period in or something. Okay, so now you bet $1 on red, 76% in a row in roulette, okay? Probably don't even know what a roulette box looks like, but a roulette wheel. But there's 18 reds, 18 blacks, and 2 greens. And you can bet on a particular color. So let's say we bet on red, and that means if you bet on red, you win $1, otherwise you lose $1. So let's make the box for a single play. So on a single play, what can happen? You either win $1 or you lose $1. Okay, so that's all that can happen. But now how many, the balls, I don't know if you've seen a roulette wheel, but the roulette wheel, but you spin the wheel and the ball, a little ball lands in one of the 18 plus 18 plus 2, 38 spots. So there's going to be 38 tickets in here. And how many ways are there to win? Well, if it lands on red, you'll win. So there should be 18 of those. And if it lands on either the green or the black, you lose. So there'll be 20 of this. So there's more ways to lose than to win. Okay? So now what would be the expected value of the sum? Because that's what we want. And this right here is our n, 76 times. So it's going to be 76 n times the average of this box, which is equal to 76 times what? So we just have to figure out the average of this box. So the average is what? Well, just add up all the numbers. And divide by 38. There's 38 numbers. So there's 18 ones plus 20 negative ones. So it's negative 2 over 38. So 76 times negative 2 over 38, which is negative $4. That's how much you expect to lose. But you're probably interested in give or take how much. You know, that's what I expect to lose some money, but, you know, am I going to lose on the average, a whole lot or not very much? And that's given to you by the standard error. So the sum of the draws is around the expected value, give or take a standard error, chance error. And how do we calculate that? And that's this very famous law in statistics called the square root law that says that the standard error of the sum of n draws depends on two things. It depends on the standard deviation of this box. If it was all ones, there'd be no standard deviation, so there'd be no error. I mean, if there was only ones in there, you'd know exactly. You play 76 times, and you get $76, and there's no standard error. So it depends on this. The bigger this is, the more spread there is, right? If you could win $100 or lose $100, there'd be a lot bigger spread. A lot. So it depends on that. The bigger the variation inside the box, the bigger the variation in the sum of your draws. But it also depends on n. And this is the most interesting thing. You'd probably think it was n times the standard deviation of the box. Just like the sum is n times the average of the box. But it's not. It's the square root of n, not n. So error scales as the square root of n. So you play 100 more times, you don't have 100 more errors. But you have only 10 times more error. So that's really important. Super, super important. And if you want to wonder why that is and want to see the proof, I wrote it as simply as I possibly could, and it's on page 226. So I think it's pretty straightforward. You can see the proof of it. Okay? So notice that as the number of draws increase, so does the standard error, but not as quickly. Right? The standard error of 100 draws will only be 10 times as large as 1, whereas the expected value for the sum will be 100 times larger. So let's look at this box right here. Okay. And now let's get the first thing you want to do is get the average and the standard deviation of this box. So the average is 5. And I'm just going to give you the standard deviation, although you could figure it out pretty quickly on your own, is 2. So now this average, another way of writing it, you can also say mu, because the box is like the population, and we're drawing random samples from it. So we're going to be looking at sampling distributions from a population. And this is sigma. But we're just going to call it the average and standard deviation of the box, but you could call it mu and sigma. Okay. So we want to compute the expected value and the standard error of the sum of 25 draws. So there's our n right there. So the expected value of the sample sum, the sample's going to vary. What do we expect to see? Well, we said that's n times the average of the box. So that's 25 times 5. Which is 125. Okay? Now, what's the standard error of the sample sum? The standard error is not n times, first of all, how are you going to remember this? Because you're not going to have this as, you're not going to have these formulas on your exam. So let's think. Standard error is like a standard deviation, right? It depends on how spread out this box is. So just write standard error, standard deviation. Okay, but it's not the standard. Each time, if you just drew once, it would be the standard deviation. But each time you draw, you're going to introduce more variation, right? So it's going to grow if you're summing things up. Each time you're going to get some chance error. But it doesn't grow as n. It grows as this square root of n. So that's how you're going to remember it, I hope. Standard error is like a standard deviation, but it's a chance process. And each time you draw, you're going to get more and more chance error if you're summing it up. So you're summing up the errors, but they sum not as n, but a square root of n. Super important that error scales as the square root of n. You're going to encounter it everywhere. If you take science class, physics, anything, you'll probably have seen this. All right, so now we've got that. So we have the square root of 25 times the standard deviation. And so that is 10. All right, so now you can see what happens as you increase from 25 by a factor of 4. What's going to happen is, what's going to happen to the expected value of the sample sum and the standard error of the sample sum? Well, you can see by the formulas here, if you increase it by a factor of 4, you are going to get 4 times the sum here, because it's just n times the average. So we're going to get 100 times 5, which is 500. So that increases by a factor of 5. But here, look what happens. Here we're going to get the square root of 100 times 2. So that only goes up by a factor of 2. Okay, only up by a factor of 2. Notice that the standard deviation is doubled in absolute terms, but halved in relative terms because of the square root law. What do I mean? In relation to the number of draws, right? 10 out of 25 versus 20 out of 100. Okay. Relative to number of draws. Okay? It's just the square root. You know, it's not going to be, we increased n by 4, but the standard error only doubled by 2. Only doubled. It didn't go by 4. That's the point. All right, now let's see. Any questions so far? So now you know how to compute a standard deviation, but there's a shortcut that's really useful if you just have 2 types of tickets. For example, just 1s and 0s. But you could have, or you could have other numbers like a -3 and a 0. If you just have 2 types of numbers on the tickets, so you could just, right? Then there's a very easy formula. If you have A's and B's, this is the formula for it. And you can see the proof for that. And that's on the page before, so that must be on page 225. All right, so let's look at this. So what's it saying? It's saying, you've probably seen this already. Instead, you've seen like, so for 0, 1 box, let me just say, so if A's and B's are for 1s and 0s, if they're for 0, 1 box, this is the same thing as, and if you've been in a previous statistics class, you've seen this. It would be 1 minus 0, or 0, just the distance there, times the fraction of A tickets times the fraction of B tickets. That fraction is just the proportion. So it would be the proportion, the percent of 1s, P times 1 minus P. The square root of P times 1 minus P. That's the same thing. Okay? How many people have seen it that way? Raise your hand. Probably a lot of people. If you change the fraction into a decimal, so this is p is equal to the fraction changed to decimal, just so you can match it up with what you know. All right, this is just the general formula for it, is what I gave you. So let's do this. So how would you find the standard deviation of this? What would you do? You'd take the distance between these two. So that's the absolute value of -3 minus 0. That's just times the square root of, there's 10 tickets total. 5 of them are one type, and 5 are the other. Okay? So it's the same thing. If you wanted to do it, you'd say, so this is 3, and this is the square root of either, you could say 0.5 times 0.5. That's p times 1 minus p. All right, and that is 1.5. That is the standard deviation. That's a lot easier than taking the average and then taking the deviations and the square root of the sum of the square root of the average deviation, of the deviation squared. All right, this is easier. So let's do this one. Okay, so this one, well, if it's 1 minus 0, that's just 1, so you don't really need it. And then it's the square root of, there's 10 tickets here. Maybe I should write this here. So 7 out of 10 have one of the numbers, and 3 out of 10 have the other. That's the same thing as, I think the p times 1 minus p is easier. Just change those to decimals. And it's easier to see that under the square root sign, even though you're multiplying, they sum to 1 because they represent 100% of the tickets here. So that's the square root of 21, which is approximately 0.458. All right. So you know how to do this. You can do the last one. So what would that be? -1 minus 8, that's 9, times the square root of, there's 38 tickets here. And 34 of them are one type, and 4 of them are the other. Okay, so that would be 9 times, do I have that written down somewhere? Hold on. Let's see if I do. Yeah, okay, so this is 9 times about 0.307, so that's 2.76. All right, let's see, how much time do we have? We should be getting on faster. Do you want to do this one? Do you want to skip this one? Do this one on your own, and I can post the answers to it? So we can move on, okay? So I'll send you a PDF, I'll post it. Okay, so do on your own. And I'll post that. Let's move on. It's just another example. Okay, and now let's do this. Okay, the expected value and the standard error of the sample average. This is super easy. We've just done the sum. Now we're just going to do the average. It's really, really easy. Okay, so you don't need any form. Okay, let's look at this. Here's an example again. All right, so here's the same thing. Average equals 5 here. We're using the same example. And the standard deviation is equal to 2. All right, so you don't need any formula for the expected value for the sample average, because why? The expected value for the sample average is just common sense. What would you expect it to be? No matter how many draws you take from here, you take with replacement, take the average, you'd expect it to be just the average of the box. The average of the population. Okay, there's nothing to compute, it's just common sense. So, all right, so you take here, you have n equals 100 draws, that's your n. We're just going to be using this and this. So your expected value for the sample average, please you don't have to compute anything. What would you, of course, what else would you expect? Why would you expect it to be any lower or higher? You take a whole bunch of tickets, you sum them up and divide by however many there are, you would expect it to be the average. In fact, the more you draw, with more draws, you'd expect it to get closer and closer to the average. So it's just going to be 5. All right. Now, but of course it's going to vary. Same way, it's going to vary depending on, just due to chance. So now, what's the rule for the standard error? How much is it going to vary? Again, it depends on the standard deviation of the box, right? So the standard error depends, let's just write it. Let's think, pretend you didn't know that. So you say the standard error equals to, what do you know? Well, you know it's like a standard deviation, right? But now, aren't you going to get closer and closer to the, aren't you going to have less and less error? I mean, if you just draw a few times, like if you just draw once or twice, you could easily get far away from 5. But if you draw over and over and over again with replacement, aren't you going to get closer and closer to 5? So instead of multiplying by the square root of n, you divide by the square root of n. Okay? So you divide by the square root of n. So now that's for the average. So now why do we do this? Before we multiplied, well, we can start here. Let's say, how do you get from a sum to an average? You divide by, let's go back to the square root law. We know this. So to get from a sum to an average, here's the average is this. We're just dividing both sides by n. That will give us this, right? Divide both sides by n. And this, if you simplify this, you can rewrite it. N is just the square root of n times the square root of n. So that's why it works. It just follows directly from the sum. Just to get the average, you divide both sides by n. And when you do that and simplify it, you get this. So that is the rule, and you're going to remember it. Because standard error, standard deviation, just think that. With a sum, it's going to get bigger and bigger and bigger, so you multiply by the square root of n. With an average, you're going to get closer and closer and closer. If you take a sample, the bigger your sample, the more accuracy you're going to have. You're going to get closer and closer to the average, and so you divide by the square root of n. It's not hard at all, so you really don't need a formula sheet, just remember that. So let's just do an example. So 100 draws with replacement from this box. You'd expect the expected value for the average, the sample average, is going to be what? Just the average of the box. There's nothing to do. So that's 5, right? Because its average is 5. But this, the standard error, is going to be what? The standard error, sorry, I don't move up sometimes. The standard error of the sample average is the SD divided by the square root of n. So that SD here is still 2, and we're going to divide by the square root of 100. So see, it's only 0.2. So you'd expect to get very close to the average. All right, let's move on. And now, whoops, I just ripped out. Is this happening to other people where you start ripping out your pages accidentally? They perforated every page. I'm going to ask them not to do that next time. Be very careful. I'm so sorry. I'm really sorry about that. Okay, so now we're going to just do one more problem for the percent. So in a classification, if you're just classifying things into males or females, ones and zeros, or category and not category, well, then we're interested in like the percent of Trump supporters, or the percent of females, or the percent of people who are going to get an A, or whatever. All right. So now, what's that? Well, that follows the expected value, first of all, the expected value of the average is the average of the box. And the expected value of the percent of like Democrats in your sample would be, you'd expect to have the same, if you're randomly sampled from a big population, you'd expect it to be just the percent of Democrats in the population. The percent's going to be the same, just like the average is going to be the same. All right? So this is just common sense. And you know what I really hate the most is when I teach and try to, and this happens a lot with statistics, that students end up forgetting their common sense. And so they come across a problem like this and they do something crazy on the exam just because somehow you're overthinking it. Please don't. Remember your common sense. Just if you have a certain percentage of Democrats in the population or a certain percentage of females in the class and I randomly sampled something from that, wouldn't I expect my sample to resemble the population that way? So please don't overthink it and get all complicated. This you knew before you entered. So now, and also, really, okay, so the standard error now, the percent of ones in n draws from 0, 1 box, if we didn't, really, the percent is just the average, right? If it's, if you think of it as a decimal, if there was, it's just the average, so it's the same formula as the average. Then we change it to a percent by multiplying by 100. This percent is a special case of what we just last learned. It's a special case of an average when you just have zeros and ones in the box. So we don't have different formulas. The only thing, if you forgot to multiply by 100, you're going to get your standard error in terms of a decimal. Like if the answer was, 3%, you'll get it as a decimal, 0.03. But you multiply by 100 to change it to a percent. Oh, that's what I say here. Okay, so you don't have to learn another formula. Just think, okay, you have to do the we just did this. Here, standard error, and you have an average. And here you have the standard error and percent, because you're going to see them both on exams, and I don't want you to rely on your notes, so what do you think? Standard error, that's like a standard deviation. So just write standard deviation. Now, for average and percents both, they're really the same. You're going to divide by the square root of n. The only time you're going to multiply is for the sum. The only difference is you see a percent here. This is your decimal. You want to change it to a percent. Like if you want to change 0.5 to a percent, it would be times 100 to add the percent sign. 0.5 is 50%. So just multiply by 100. I'll put a percent there to remind you that you're changing it to a percent. That's all there is. Okay, so now let's suppose you draw at random with replacement from this same box. I don't think we did an example. Let's just say, I think it's just the first time we see this. Okay, you're interested in the percent of 2s you get, okay? We didn't just do an example like this, so this must have been cut and paste from something. Okay, so now, first, change the box to a 0, 1 box. All right, so we want to change this to, we're just looking at the percent of 2s. So if we get a 2, like these, if we get a 2, we change them to 1, 2. It's like counting, right? But if we get anything else, it's 0, 2s. Okay, so now we have a 0, 1 box. Now, what's the expected value of the percent of 2s? Well, it's going to be the same. The expected value of the percent is just going to be the percent in the population. It's going to equal 50% because 50% of the box, you could have seen it from here, 50 is 2s. All right, so you don't have to do anything there. But now, the standard error of the sample percent. All right, so write it down without always write standard error, standard deviation. Now, you know to divide by square root of n and then times 100. All right, so what do we have there? Well, we don't know the standard deviation yet. The square root of, how many times are we drawing? Where does it say that? 36. So it's going to be the square root of 36 times 100. We just have to get that standard deviation. All right, so standard deviation of the box. Well, here's our box. It's 0 and 1, and it's 50% and 50%, right? So do you remember how to get the standard deviation? It's just the numbers on the tickets is just 1 minus 0. We can forget about that. Times the square root of, you could say 1 over 2, but it's easier just to think of p times 1 minus p of 0.5 times 0.5. 5 over 10 times 5 over 10, or 0.5 times 0.10. So this right here is the fraction, or the fraction of ones in the box. And this is the fraction, or the proportion, of zeros in the box. And they have to add up to 100 under there. You're multiplying, but they have to. So you get the square root of 0.25. Square root of 25 is 5, so this is 0.5. And that makes total sense. If you think of what a standard deviation is, the average of 0 and 1 is a half, 0.5. And this is 0.5 below, 0 is 0.5 below, and 1 is 0.5 above. So you have two deviations, and they are both 0.5. So your standard deviation has to be 0.5. All right, so we've got that. So that's what we put here. Up here, we get 0.5. Okay, and this times 100, and I'll put a little percent sign there, and that is 8.33%. All right, maybe we have time for another iClicker. I want you to think about this. Think about this calculation right here. When you have a 0, 1 box, this is always going to have 1 minus 0, so you're just thinking about this. And I want you to think about what the largest and what the smallest, the standard deviation of a 0, 1 box can be. That's the iClicker question, so let's go to it. And okay, I'm going to stop it now, so just pick one. And let's see what you answered. The answer is B, and let's see what people did. Good, that was the most common answer. Now I'm going to ask you, you can think about it, it has the most uncertainty. Standard deviation, that measures uncertainty. When it's half one, half the other, you have no idea, If it's all of one, you're pretty certain, right? Or the more, just do the math, do the square root of 0.5 times 0.5. That's what? The square root of 0.25. What if it was an 80%, 20% split? That would be 0.8 times 0.2, square root of 0.16. What's the square root of 16? 4, so you have 0.4. So it keeps going down. If there's a 10%, 90% split, you'd have this, it would go down to 30, right? So it keeps going down. You have the most uncertainty if it's half one, half the other. You have the biggest spread. Okay, let's do the next question as the iClicker. The next one is, I gotta click there. Okay, I'm gonna start this one. You should know this one now. Okay, we'll stop it right here. And let's see what you said. Great. That's it. That's perfect. And if you did the math, it would be the square root of 1 times 0. Square root of 0 is 0. Whether, doesn't matter whether it's ones or zeros. You're certain, you're absolutely certain. If it's all ones, you know you're going to get a 1. You're going to have no variation. There's no spread. Same if it's all zeros. The average is 0. Here the average is 1. You have no deviations. Great. Okay, let's go now to the next chapter. We're going to put this all together with the, okay, so this is all summaries. And just to remind you, standard error formulas. Standard error is a standard deviation. This is on page 50. And the only thing you have to think about is for the sum, you multiply by the square root of n, and for average and percents, you divide by the square root of n. Okay? So now let's move to our next page, and we're going to do, try to get through this. So what are we going to be doing here? We did our statistics, the expected value and the standard error. Now we're going to draw what's called probability histograms. They're just like the histograms we drew for lists of numbers, but now a probability histogram is going to just, still going to sum to 100%. It's still going to list here all the possible outcomes drawn to scale. All the possible outcomes, and you have to draw them to scale because this is going to be a histogram. So if you have outcome of 1 in 100, they have to be 100. The distance has to mean something. And these here will just be the density or the probabilities for each possible outcome. So we have this amazing, this is one of the most important theorems in all of statistics, the central limit theorem. That, along with the square root law, which we just saw, those two are probably the two most basic theorems in all of statistics. So what does it say? The central limit theorem says that the probability histogram of all possible sums, which means you just divide by n to get an average, or percentages, right, of draws from a box, like the sampling distribution, like of all, what the distribution of all the possible sums or percentages are going to look like, is going to look like the normal curve as the draws get bigger and bigger and bigger. So the number of draws do. So let me illustrate this, and so you understand what this is. So let's just draw the probability histogram for tossing for the number of heads on 1, 2, 3, 4 tosses of a fair coin. And what the central limit theorem says is the number of tosses increases, that probability histogram is going to look more and more like the normal curve. So with just n equals 1 toss, we just have 2 possibilities, a 0 and a 1, with equal likelihood. So if we want to draw what the probability histogram looks like, we just say, okay, there's only 2 possible outcomes, a 0 and a 1, and they both have the same likelihood. I'm just making them each 1 unit wide, and that likelihood is 1/2, or 50%. And that's all it is. That's the probability histogram. It does not look like the normal curve yet. Now, for 2 tosses, what does it look like? Well, here there's 2 possibilities. Then now there's 2 times 2. Because think about it. Here's your possibilities for 1 toss. And now we're summing them up. Let's do our second toss. We could also get a 0 or 1. And we're going to be summing those up. So 0 plus 0, if we get a 0 heads on the next toss, that's what we're going to end up with in terms of number of heads. Or we could get another head, or a head. And so those are our possibilities. We could get 0 heads, 1 head, and there's 2 ways to do that, or 2 heads. So now we're going to draw that here. So now we have 0, 1, and 2. but they're not all equally likely, right? Here's our 4. 1 out of 4 times we'll get a 0, and 1 out of 4 times we'll get a 2. But look, 50% of the time, there's 2 ways to get a 1. Now remember, it has to add up to 100%, all histograms do. So this is 1 out of 4 ways, and this is 1/2. So that's what it would look like. Now let's do 3. You'll see how it starts looking more like the normal curve. So now it's 2 to the 3rd, right? 2 ways, the first one, 2 times 2 times 2. So now we'll take, after 2 tosses, these were our 4 possibilities. That's how many heads. Now we flip the coin again, and if we could either get 0 heads or 1 head, a tail or a head. If we got the tail, we'd stay the same. If we got a head, we'd just add 1 to these. So now we have 8 possibilities, 0 and 3, and we can draw it, and you're going to see it's going to look more like the normal curve. So we'll have 0, 1, 2, and 3. And there's 8 possibilities. Only one of the 8 is a 0 and a 3. So make those the same height, 0 and 3, and that's 1 out of 8 times. And for a 1, there's 3 ways for the 1 and 3 ways for the 2, so make that 3 times as tall. And 3 times as tall, they're all the same width, and that's 3/8, and it adds up to 1. All right, now let's do the next one here. I'm not going to keep going. This will be the last one. So now there's 2 to the 4th possibilities. So we can write out our possibilities. 0. There's 1, 2, 3. So now we'd have the same ones. If we get a tail, but if we get a head, we're just going to add 1 to all those. All right, so now it could range from from 0 to 4. So we have 0, 1, 2, 3, and 4. And there's 16 possibilities, and there's only 1 out of the 16 is a 0, and 1 out of the 16 is a 4. And then 1, 2, 3, 4 are 1s and 4 are 3s. So make that 4 times as high. So those are both 4 out of 16. And then the most common is a 2, and there's 6 of them. Okay, so another way, instead of doing all this, another way for counting the number of k heads out of n tosses. So that's n choose k. You might know that's another way of writing that. And what it is, I don't know, I'm not going to go into detail, but if you've already had this, it's n factorial over k factorial times n minus k factorial. And that's another way, for example, to get the 6 heads. For example, I'll show you. So 4 to get these, how many ways there are to get 2 heads on 4 tosses. So we just say that's n factorial. So that would be equal to 4 times 3 times 2 times 1 over 2 factorial, which is 2 times 1, over 4 minus 2 factorial, which is 2 times 1. So that's where you get 12 over 2, which is 6. So you could check it that way. You're not going to be tested on this, and we need to move on, but that's just, you've probably seen that in another probability class, and if you're interested in more work like that, we could do it, but for this, we're not going to be tested on it or have homework problems. All right, now what I wanted to illustrate though was this beautiful central limit theorem. See, as the number of tosses increases, the histogram looks more and more like the normal curve. Does it? Yes, it does. And I don't have time to show you this, but in your homework you can look at this, and I have a link to it. how you can look at this in the homework. But now we have to move on. We might be able to get to it next time. All right, so now, so what's really cool about this is I said, no matter what the original box looks like, it can be really skewed, it can be any type of distribution inside the box. The central limit theorem says that eventually, as the number of draws gets more and more, the probability histogram for the sum, average, or percent will follow the normal curve. So how many draws is enough? Well, that depends on how close the original box follows the normal curve. So here's two examples. Okay, so here you have box 1 and box 2. All right, draw the histogram of the contents of each box. Which differs more from the normal curve? The contents of the box is just like one draw from the box. These all have the same probabilities, 1/3, but they have to be drawn to scale. So 1, 2, and 3. This box just has this uniform distribution with no gaps here, and it's all, each one is 1/3. This one each has a chance of 1/3, but it's not, look at this, we have to draw this to scale. So if we did that, it would be 1, you have to do 1, 2, 3, 4, 5, 6, 7, 8, 9. So now the first two are going to look the same. That's 1/3, but this one's way over here. So which differs? B, this one differs. Because, why? It's uneven, very uneven, so it will take more draws for the central limit theorem to kick in. And we're going to be using the central limit theorem to figure out probabilities for these random variables. Uneven because more draws, so uneven, so more draws are needed before the probability histogram for the sum, probability histogram, will look normal. And you can see that right away, okay, just on 2 draws and taking the sum. 2 draws and taking the sum, 1 plus 1, you're just going to add 1 plus 1 is 2, 3, 4 here, and this is 3, 4, 5, and 4, 5, 6. 3 plus 3 is 6, so this is it. And if you draw, these are the possibilities, and here they are, and let's look at it. There's one way, you can't get a 1 at all. The smallest you can get is 2, and the largest you can get is 6. And for each of those, there's only one way that can happen, 1 out of the 9, so that's 1/9. And then there's 2 ways you can get a 3 and a 5, so that should be twice as tall and twice as tall, so that's 2 out of 9, and then there's 3 ways you can get a 4. So doesn't that look normal already? But now if we try to do the same thing here, what happens? Here we get 2, 3, 10, and then we get 3, 4, 11, but now when we add these up, we get 10, 11, and 18. So there's 9 possible for each of them. For each of them, it's going to be equal to 9 possible outcomes for both of them. But it's not going to look normal here. Because what do we have? We have 1, 2, you can't get a 1, 2 3s, so we'll make that a little bit taller. So that's 1 out of 9, that's 2 out of 9. Then what do we have? 1, 4, so that's the same. There's also 118 way out here, so those are all 1 out of 9. Those are all 1 out of 9. What else can we get? A 10, a 10 and 11. And there's 2 ways to get both of those. So make it like as big as go up to 2 9ths for 10 and 11. And that's our probability histogram. Does it look normal yet? No. But the coolest thing is it will look normal. It will. So, and here from our Now look at the probability, blah, 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 sorry. Now look at the probability histogram for the sum of 25 and 50 draws from these same boxes. You see? Now which is which? You can see right here, this middle number, n times the average of the box. The average here is 2. The average here is 4. You can see that these two come from box A, and these two come from box B. Here, look. This 25 right here, 25 draws here. That's the middle number right here is n times the average. So in that, it's n. The middle number here is n times the average. And the average of this box is 2. And the average of this box is 12 divided is 4. So you see how that's going to be. The middle's going to be. Also, this one has a bigger standard deviation than this one. So it's more spread out. Let's see what's coming up. All right. Now we're going to have time to actually do this, and so you'll be able to do your homework. All right, so now we're going to do, look, Z. We're going to do the normal approximation for random variables. So this right here is the z-score formula for random variables. Instead of average, we have expected value, and instead of standard deviation, we have standard error. So let's do one example, and then you'll be able to do your homework. Oh, sorry, z-score formula for random variables. All right, so let's look at this. In 100 coin tosses, what's the chance of getting between 40% and 60% heads? 2 to the 100th possibilities, that would be crazy. We couldn't think of it that way. So let's just do the normal approximation. All right, so we draw the box. We already know this box for a single toss. So we have a 1 and a 0, right? Just 2 tickets, it's a 50%, 50%. Okay, so that's what we're going to be doing. Now, n is equal to 100. Where does that come from? That, and that's with replacement. Okay, so now the expected value for, what are we doing? The percent. Okay, for the sample percent. Okay, well, that's just going to be 50%, same as in the box. But now we're going to do the standard error for the sample percent. And what is that? Okay, that is going to be equal to, you should know this, just write down standard deviation, and then you divide by the square root of n, multiply by 100. Okay? So we have 100 tosses, right? That's the n. And the standard deviation of this box you should know. If you didn't, you could just say the square root, the SD is equal to 1 minus 0 times 0.5 times 0.5. But you should know it. All right? And that is 5%. So we'd expect 50%, give or take 5%. Now, what are we going to do here? We are going to convert our endpoints to z-scores. So let's do that. We want to just change those to z. So z equals our value minus the average usually, but it's the expected value for a chance process, and we're talking about percents. So this is really easy. This won't take us long at all. Z for 40% is going to be equal to what? 40, our value, minus 50% over 5. So that's negative 2. And Z for 60% is going to be equal to 60 minus 50 over 5, which is positive 2. All right, so here we have 0, 1, 2, negative 1, and negative 2. And it lines up, obviously, with 50%. And our standard error was 5, so that's 55%. And here's 60%. 45% and 40%. And between 2 and negative 2 on the normal curve is approximately 95%. So there's our answer. And let's do one last iClicker so I can just make sure. And it's super easy. And here is your iClicker question. And actually, it's really simple. I'm going to start it right now. You can, if you want to see what it is, that's not it. How come I can't go down? Damn, what happened? I'm rushing. Just answer anything. I'll tell you what the question is. The question is, are you asleep? Yes? A. No. Are you asleep? Maybe. A, B, or C. Just answer A, B, or C. It's just to see if you're still here. The question was like, are you asleep now? But it disappeared. So just answer. Get your thing up here. Just say anything. A, B, C. I don't care. D, E, whatever.